Okay, so I want to go through chapter 18, which deals with something called sampling distributions. This chapter is really important for and lays the groundwork for everything we're going to do in the remaining time we have in this course. So you should have notes of this so you can just follow along and we'll start talking about it now. I know I need a new example, but The Walking Dead is still a TV show. I used to watch it, but I don't anymore. I liked it when they were just fighting zombies, but not each other. So suppose we want to know the proportion of adults in the United States who watch The Walking Dead. The true proportion that describes the population is called a parameter. And in statistics, the parameter is not known. If it was known, we wouldn't need statistics. So we want to know what the true proportion is. Since we don't know the parameter, we use sampling techniques to estimate the parameter. A statistic is a number that is calculated from sample data without making use of any unknown parameters. This statistic estimates the parameter. So we're gathering a sample, and it needs to be with the sampling techniques we talked about earlier in the course. And then from that sample, we calculate a statistic, which in this case is going to be a sample proportion. And then we use that to estimate what we think the true proportion is. So for example, if a telemarketer firm in Columbus uses a device that dials residential telephone numbers in that city at random, of the first 100 numbers dialed, 48% are unlisted. This is not surprising because 52% of all Columbus residential phones are unlisted. And then I'm asking that you identify each percent as a statistic or a parameter. And if we were in class, I'd call on somebody. But here, we know that what's being said is the true amount, is that 52% is the true amount, but we wouldn't really know that. And then 48% is the statistic that comes from a sample. Suppose that in fact 30% of the population of all adult U.S. residents watch The Walking Dead. Then the true value of the parameter we want to estimate is p equals 0.3. And I make a little disclaimer, of course, we would not sample if we already knew that p was 0.3. We're just doing this to see how sampling behaves and what we can learn from that. So we are just making this assumption that it is that the proportion of people who watch the Walking Dead in the U.S. is 30%. So what we could do is do a simulation. We've talked about doing those before. We could take a simple random sample using table B. We could let 0, 1, and 2 represent watching The Walking Dead, so picking 3 out of the 10 digits, and then 3 through 9 not watching. And then I make a comment, by the way, what distribution does this have? They either watch The Walking Dead or they don't watch The Walking Dead. The probability of them watching it is 0.3 for each time, assuming that we have independence, or so you should hopefully recognize that this actually looks like a binomial distribution. So if we were simulating this, if you started at line 120 and you took a random sample of 20 and those are the digits, so 3 would represent not watching, 5 is not watching, and you can see what you would end up with would be 4 out of those 20 people from our simulation, we would say watch The Walking Dead. So our estimated proportion would be 0.2. So if we repeated another sample, would we get the same results? Well, no. That's because of sampling variability. The value of a statistic varies in repeated random sampling. So if we did it again, we'd get another p-value. If we did it again, we'd get another p-value. So the procedure for estimating p, by the way, just like the sample mean, we've dealt with that before, was x bar. The sample proportion is going to be p hat with the little, upside down v on top, p hat. So here's the procedure. You take a large number of samples from the same population. You calculate the sample proportion p hat for each sample. I couldn't spell out the p hat like that, so I had to write p hat. Make a histogram of the values of p hat. And then examine the distribution displayed in the histogram for overall pattern, center and spread, outliers, or other deviations. Suppose we want to take a simple random sample of size 100 from the adult population. Further, suppose we want to repeat this 1,000 times. We definitely don't want to use a random number table. That would take a really long time. I used Minitab, which is a computer software, and made it much simpler. So again, keep in mind what this means. A sample of 100 adults and calculate a p-hat value. Sample 100 more adults, calculate the p-hat value. Take a sample of 100 more adults, calculate the p-hat value. Do this 1,000 times. Yeah, by hand? No. So here are the results of 1,000 trials with sample size of 100. So if we were to look at the center, shape, and spread, notice actually on this shape, it's approximately normal. Looks very symmetrical. My center then is going to be right about here in the middle. So notice it looks like it's about 0.3. Shouldn't be a surprise because that's the assumption that this was built on. And then the spread, it looks like it goes from about 0.15 to 0.45. So think also, because this is approximately normal, and we know that there would be 3 standard deviations, should cover pretty much all the data. So if 0.3 is in the middle and 0.45 is on the upper end, and that covers 3 standard deviations approximately, you can take the difference, which is 0.15, and divide it by 3. So this would appear that the standard deviation looks like it's about 0.05. Didn't really have any outliers, so anyway, that would be the center, shape, and spread. So it looks approximately normal, got the center, the spread, there's no outliers, and notice the standard deviation. My estimate was about 0.05, and that's actually what it was. This came also from the Minitab software that I used. Suppose I alter my sampling. This time we're going to take a simple random sample of size 2,500 and repeat the sample 1,000 times. That would be like contacting 2,500 people and asking them if they watch The Walking Dead, then calculate the sample proportion, contact another 2,500 people, then contact another 2,500 people, and we would do this 1,000 times. And this is why simulation is very helpful, because normally when you are taking a sample as an actual statistician and you need to take a sample so you can make some type of inference, you only get one shot at it. You don't get to do 1,000 samples. You get to do one sample. So we want it to be a good sample. So here are the results. And I did it on the same scale. Notice that the scale is the same. If we described the sampling distribution, the center appears to be about 0.3. The shape appears approximately normal. And the spread, notice, is much, much smaller. You can calculate it if you want. I'm going to show, and there's no outliers. So here is the value for this. Look at the standard deviation. So notice that the p-hat value didn't really change very much. And so the center really doesn't change. It's the standard deviation that is so surprisingly different. And here, which is the answer right here. You look at the change in the spread. Now remember what I said. If you take a sample and you really wanted to know the true proportion, you get one shot. So let's say you only did 100 people and you took your sample, and you might be lucky and get the 0.3 and have a good estimate. Or maybe your one sample you do, maybe you actually end up with one of these 0.45s, because it's possible. And you think, oh, wow, 45% of the people are watching The Walking Dead. So what do? Well, if you own a TV company that is showing The Walking Dead, you're going to charge more for commercials if you can show that more people watch it. Well, if then it's found out, oops, yeah, we were really off. It was really only 0.3. Then those companies are going to sue you because you've charged them too much for these commercials. Okay, on the flip side down here, maybe your one sample is like close to 0.15 and you say, oh, that's how many people. So what happens? You don't charge as much for advertising. The companies that are advertising are happy, but so there's a lot of implications that can happen because you only get one shot at it. But look up here. If you take a sample size of 2,500, and maybe you're at the upper end, well, you're still below 0.35. Or if you're at the lower end, you're still above 0.25. So it's more consistent when you take a larger sample size. So that matters. And we have to think about that before you take your sample. So when the sample size is increased, the mean stays approximately the same, but the spread is much less varied, and we like that. because then we know we're more accurate. We also need to look at what's called the bias of a statistic. A statistic used to estimate a parameter is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So we don't want it to be unbiased. So the goal of an archer is to hit the target. What does this have to do with statistics, you ask? Maybe you didn't ask, but I'll tell you anyway. So you could have high bias. Maybe the sample proportion misses the parameter in the same direction each time. So here's the parameter here, the true value, and we are hitting up here all the time. Now that can happen if you have a bad question. So maybe there's something wrong with your sampling methods, and so you end up with bias when you are trying to calculate your parameter. But we have low variability here. There's very little spread, so we're consistently wrong, I guess you could say, which is not a good thing, because then you think this is the true parameter if you don't realize that it's biased, so you have to pay attention to that. Or maybe you have low bias, which means the sampling distribution hits the center of the target. Notice here's the center, the true proportion, but you have high variability. There's a lot of spread in the sampling distribution of p hat. That's what we saw when I did the sample size of just 100 instead of 2,500. We had that issue. And you might actually think, well, then maybe I should just always do a really large sample. Well, there's problems with that too, because remember how we've talked about in issues of satisfying independence, for a finite population, that you can't exceed 10% of the population. So sometimes that's an issue. Your sample size can't be too big, and so you can't just always say, I'm going to take a huge sample. Another reason you can't always just say, I'm going to take a huge sample, is maybe you are doing taking a sample because you want to check the effectiveness of a new medication, but the medication is super expensive. You might not be able to take a really large sample because you don't have the money to do that with this medication. So, other things to think about. So you can have high bias, the sample proportion misses the parameter in the same direction each time, and high variability, there's a lot of spread in the sampling distribution of p hat. And you can see how that's just bad and bad. Or you can have low bias, the mean of the sampling distribution hits the center of the target, and low variability, there's very little spread in the sampling distribution of p hat. And as you can see, that makes us happy. So some final notes. The spread of a sampling distribution is determined by the sampling design and the size of the sample. Larger samples give smaller spread. As long as the population is much larger than the sample, say at least 10 times as large, the spread of the sampling distribution is approximately the same for any population size. And that is pretty key. So what that's saying is it doesn't matter the population size. If you are trying to estimate the true parameter of everyone in the United States for something, and you take a sample of, say, 2,500, you're going to get just as good results as if you only wanted to know, say, the state of Ohio, and you took a sample from the state of Ohio to find out their proportion. So even though the population is much larger for the United States than it is just for Ohio, as long as our population is at least 10 times larger than our sample, which in both cases that would be, then you get a good estimation, equally good for both of them. So that's important to keep in mind as well. And that is the end of, well, I shouldn't say the end of Chapter 18 because we're going to be on Chapter 18 for a while. That's the end of this presentation, so our little kind of intro into Chapter 18. So that's it.